Welcome back to Sampling and Experimental Design. So in today's lecture, we are going to look at the randomized block design model again, this time in the context of two factors composing the treatments. Okay, so we're going to start with just a quick recap of what we've called RBD, Randomized Block Design Model. So let's call this two factors with blocking. Okay, so let's first write down the randomized block design model, and then let's take that, and from there we will look at it as an interaction and two-factor model. Okay, so start with randomized block design model with T treatments. And in our context, when we did randomized block design, we only have one replicate for each treatment and block combination, so we'll keep the same setup here. So one rep per block. Okay, so the model looks like this. So we model the response. That's y, so for the ith treatment, and the jth block, so yij, modeled as an overall mean parameter plus a treatment effect, so that's the index I, and then plus a block effect, that's the index j, and then plus a residual term, which is assumed to be all independent and normal with the same variance. Okay, so the treatments, we can number them 1 to t, and then the blocks we can number from 1 to b. Okay, so now we're going to take our t treatments again, and let's now suppose that the t treatments are a combination of the levels of two factors. Let's call them factor A and factor B. Okay, so in that case, we can take the RBD model and we can rewrite it using factors and interactions. Okay, so when the treatments are a combination of two factors, okay, so it's called the two factors A and B. Okay, so we're going to assume A has T sub A levels and B has T sub B levels. So in other words, total number of treatments is the combination of these two factors, so T sub A times T sub B. Okay, so very much like the analog of the block analog of the model we looked at in our last lecture, which was where we had a CRD and then we looked at the treatments as being a combination of two factors. So now we're looking at the same idea, but it's now in the context of randomized block design model. Okay, so let's suppose the T treatments are a combination of these two factors. Okay, and so as in our last lecture, we can then take this model, which we learned before, and re-express it in terms of factor and interaction parameters. Okay, we can express the model with effects for the factors A, B, and their interaction. Okay, so it's really taking what we learned in our last lecture and applying it in the same way to the randomized block design model. Okay, so how would we write it? Well, again, we're going to take the treatment effect term, that's the tau i's, and we're going to decompose that into three parts: the main effect of A, main effect of B, and their interaction. So we're going to use the same notation for those three sets of parameters. Okay, so so this is what the model would look like. So y. So now by rewriting, we now have three subscripts. I and j refer to the levels of factor a and b, and then now k is the index for the which block we're in. K would go from 1 to b. Okay, so we're basically copying down this model. So mu, you just copy down, and then what this model does is it takes the tau I parameters and rewrites it by decomposing it into three sets of parameters: the alpha, lambda, and the gamma parameters. Okay, so that's the same idea as in the interaction model. Okay, so we now have alpha I as the effect of level I of factor A, and then we'll use lambda j to denote the effect of level j of factor B, and then we're going to have interaction parameters gamma ij for the ith interaction between the ith level of A and the jth level of B. Okay, and the block term we're not going to do anything with. We're just going to assume the block has an additive effect. Okay, so now we've just as a point of reminder, we've seen what we call an additive effects model, and compared that to an interaction model. So when I say the block effect is additive, we understand that we're assuming that the block doesn't interact with any of the treatments. Okay, and so therefore the effect of the jth or the block it can simply be added on to the treatment effect. Okay, so now since the block index got shifted to k, so the block will now be indexed as beta sub k, and then for each unit in our experiment, so for each unit assigned to the unique combination of level I of A, level j of B, and block k, it would have its own independent residual term. So we now index that by r sub ijk. Okay, so this is the same model as the RBD, but we've taken the tau parameters and we have decomposed it into these three sets of parameters governing the main effects of A and B and their interaction. Okay, so let's just make sure we spell out all the notation here. So I goes from 1 to t sub A. So these are for the levels of A. J goes from 1 to t sub B. Those are the levels of B. And then K goes from 1 to B. And these are the blocks. And then finally we have our sub ijk, which is the residual term, and that is assumed, as in all of our models, that they have an independent normal 0 and the same variance sigma squared. Okay, so there's a question that says, do we want all the residuals to add up to 0? So from a model construction point of view, all we're assuming is the residual on average has 0. Okay, and now what the residuals actually sum up to when we fit it as a linear model is they do from the after estimation they do sum to 0. Though that would not be a key thing to remember here, because this is looking at it as a model setup. And we're imposing this as a model assumption, not necessarily on the data. Okay, so we're assuming the residuals are all normally distributed with 0 means. So on average, in other words, we're saying that on average the fitted value is going to match the observation, and then with the residual normally distributed with variance sigma squared, and this is the same sigma squared for all the units. So no matter what treatment combination you receive and which block you're in, we're assuming they all have the same residual variance. Okay, so other comments here is that now beta k is the block effect. So let's add that here. So beta k is block effect, and we assume, and as I mentioned, we assume it is additive, and so in other words, it doesn't. In other words, we're assuming this block, the blocking variable, does not interact with either factor. Okay, so we're not doing like some. We can exhaust the Greek alphabet here by doing a, say, for example, another term that is k block interacting with factor A, block interacting with factor B. So we could hypothetically extend this model a lot further, but we're going to assume that the block simply does not interact with the two factors, and so we're not going to put an interaction term. We're not going to put any additional interaction terms in this model. Okay, so assume is additive, and which we now understand to mean it does not interact with either factor. Okay, so the next thing I want to look at is, of course, we have a lot of parameters in this model, and so there is also a lot of constraints. So let's list them. So we have them available. So let's do it here. So let's list all the constraints on the parameters. Okay, so some of them are the same ones that we have seen before. Okay, so for each of these, so the three easy ones are for these effects for factor A, factor B, and the block. Okay, they only involve one subscript, so we can just apply what we learned from before. We know that the constraints is that these three individual sets of parameters must sum to 0. Okay, so let's start with those. Okay, so summation I goes from 1 to the levels of A, alpha I. Okay, so that sums to 0. The sum of the lambdas is also 0. And then the block effects also sum to 0. And remember that these constraints are what allow this model to be interpretable. Okay, so that's what allows mu to represent the overall mean, and for each of these parameters to have their corresponding interpretation. That alpha I is how much the level I of factor A changes the average compared to mu. So that's how we get all those usual interpretations. They are because of the parametric constraints. Okay, so block effects sum to 0. Okay, so that takes care of these three these three sets of parameters. And then finally we have the interaction parameters, and so the same constraints that we saw in the interaction model also apply here. Okay, so let's write it out again. So we have it all in one place. So interaction parameters. So the constraint on that is that if I sum over I, so I sum over the first index of the interaction parameters, gamma and j, that's going to be 0 for all j. Okay, so for any index j, this sums to 0, and then you flip the indices. So if you now sum over j, those interactions also sum to 0 for all I. Okay, so gamma ij. So pretty easy to remember the symmetry here. So no matter which index you sum over, for all values of the other index, the interactions need to sum to 0. Okay, so that's for all I. Okay, so that's the basic model setup. So we've taken, just to recap what we've done so far, we've taken the randomized block design model, and we're taking the treatment effect parameters and decomposing that into the two parameters for the two factors, and also for the interaction. Okay, so the next step, as we've always done, is to look at the parameter estimates. Okay, so let me leave this model up for the time being and write down how we do estimation. Okay, so with that model here on the board, we can figure out from here what is the least squares expression that we're going to do using constrained optimization. So estimation. Okay, so now we're minimizing. We're finding the set of parameters that minimizes this least squares expression over. Now there's a pretty long set of parameters. So there's mu, there's alpha, lambda, gamma, and beta. So over all of these parameters. So least squares expression. So you're taking the observations. So y of gk. Taking each of the observed once you have the measurements, and then we're subtracting what the model is predicting, so it's everything here. For all of these parameters are fitted to the model, and so if you're in the level I of factor A and level J of factor B, and then block K, then these 5 parameters added together is what the model is predicting for your response. So that's what we're minimizing, that difference. So let's just write all of these parameters over here. Oh, I forgot to write the summation, so let's try that again. So summation over all levels of A, B, and blocks. Okay, so just for compactness, I'll write it. It's really a triple summation, but I'll just write it. It's clear that what the indices are summing over, and so what we're minimizing is this difference of minus mu alpha I lambda j interaction and then block. And so we're doing that subject to all the constraints. Okay, so that's our usual least squares expression. Beta, yes, I missed a subscript here. Beta k, thank you. All right, yeah. So 5 sets of parameters here. So that's all goes on here, and then we minimize this sum of squares. Okay, so what are the estimates? Well, many of them are actually exactly the same as in the interaction model. So let's just take a shortcut and just use that result. Okay, well, of course, to mention how we do it, well, this can be done using, it's a constrained minimization, so we can do it using an extension of Lagrange multipliers, although there's, I will skip those details here. Okay, so the estimates, so I will again skip the details and just say mu hat. So 4 of the parameters, 4 sets of those parameters, so the mu, alpha, lambda, and the interaction parameters are exactly the same as in the 2-factor interaction model. Okay, so same as 2-factor interaction model that we saw without blocking. Without blocking. Okay, so those formulas are a little bit long, so I won't rewrite them here. So the only new set of parameters that we need to estimate here is the block parameter. So I will write that estimate. So that's beta k hat. So the effect of the kth block is actually it's the same form as we saw before. How do we estimate the block effect? We take the average of all the units in block K and then subtract the overall average. Okay, so all the units assigned to block K, so we're going to do y bar. So the block is the 3rd subscript, so we're averaging over all the units in block K. So this is the block average, and then subtract the overall average. Okay, so this is exactly the same it's actually exactly the same formula as we saw in randomized block design. It's the block average minus the overall average. The notation just looks a little bit different because instead of having just one subscript before the block, we now have two because we're now writing out factor A to B explicitly. But otherwise, it's exactly the same block effect estimate. Okay, so that's the only new estimate formula that I need to give you. So now, once we have the parameter estimates, we need to write down the estimate of our residual variance on sigma squared. Okay, so before we do that, we need to do a quick recap of what would be the degrees of freedom of the residual. Okay, so to remind you, how we get the degrees of freedom is we take the total sample size and then we subtract all the free parameters. Okay, so at first glance, you might think, well, but there's a lot of complicated constraints here, so how do we count the free parameters? Well, fortunately, we can use the same trick as last time, and remember that this is simply another way of writing the randomized block design model. Okay, and so therefore, it must have the same residual degrees of freedom as the randomized block design model. Okay, so we can therefore get the degrees of freedom immediately without actually having to count through all the different constraints. Okay, so therefore, let's write it here. So the residual degree of freedom is, okay, so what was it in randomized block design? It was T, the number of treatments, one less than T, one less number of treatments times one less than the number of blocks. Okay, so this is the result. This comes from randomized block design. Okay, so the only thing we might do is write it a little differently because now the treatments T is expressed as the treatment combinations of A and B. So the only thing we might write differently is to rewrite this as TA times TB minus 1, and then B minus 1. Okay, so we were able to get the correct residual degrees of freedom that we need to use without having to do any additional work by remembering that this is simply another way of writing the RBD model. Okay, so once we have that, we can write down the actual estimates for the residual. So let's do sigma squared hat. Okay, so we need to do 1 over residual degrees of freedom. So let's copy that down here. TA, TB minus 1, box minus 1. And then we need to do the, so 1 over degrees of freedom, residual degrees of freedom, and then we have the residual sum of squares. Okay, so it's nice we have this expression from the least squares because we basically just copy it down and just put hats on all. Now that we've estimated all the parameters, we put all the hats on those 5 sets of parameters. Okay, so this time I'll just write it out in full. So it's clear that we're summing over the I is summing over the levels of A, J is summing over the levels of B, K is summing over all the blocks, and then in here we have the least squares expression after we've computed all of the estimates. Mu hat, alpha hat, lambda hat, interactions, and then the block. Okay, so that's the estimate for residual variance. Okay, and so just like before, we can plug in all the estimates we have now found for these 5 sets of parameters. So we can plug in everything and then simplify. So I'll just give you the simplified expression. So after plugging everything in, this can be reduced in terms of the y's. It's the observation minus the treatment mean. So this is recall y bar ij dot is a treatment mean because it is all the units assigned to level I of A and level J of B, and so that is one specific treatment, and so this is the mean of that treatment. Okay, so minus the treatment mean and then minus the block mean, and then finally plus the overall mean. Okay, so actually, this expression is it's just a different way of writing the residual for RBDs. Okay, so in RBDs we had the same. It's the same thing, but it's just written with different notation because we've broken up the treatments into the two factors. Okay, so in words again, it's the observation minus the treatment mean minus the block mean plus the overall mean, and that's exactly the same expression in words as what we saw in RBD. Okay, so that is the residual that is the residual term. Okay, so next we need to do a sum of squares decomposition. So fortunately, again, there's actually no new math here. We just take decompositions we've seen before, and then we just combine them, and then we can get a decomposition for this case as well. Okay, so starting from the treatment sum of squares. So now the treatment sum of squares looks like this. It's the same treatment sum of squares formula, except instead of R replicas we have B blocks. So just change the B to an R. Otherwise, it's the same expression. So sum over all the treatments. So in other words, all combinations of I and J. Treatment mean IJ dot minus the overall mean. Okay, so that's always the treatment sum of squares. Take all the treatment means, subtract the overall mean, and add them up. And then instead of R, we now have B. Okay, so this is the treatment sum of squares. Just like in the two-factor interaction model, the treatment sum of squares decomposes into a sum of squares for factor A, B, and their interaction. And so it's exactly the same formula. Instead of having R, I just now have B. So let's go ahead and write that down. So we have the sum of squares for factor A. Okay, so how do we get A? So A is the first subscript, so summing over all the levels of A, so I dot dot, so averaging out everything else. Difference from that, the overall mean. Okay, and then the second term is for factor B, so now I have the average for the level of factor B. And then finally, the interaction term. So let's put it here plus so let's see if I can fit the interaction term in here. It's y bar. So the treatment mean minus the factor A mean minus the factor B mean, and then plus the overall mean. Okay, hopefully you can see that. It's exactly the same expression as the interaction sum of squares when we had just the two-factor interaction model. Okay, the only change is instead of R replicates, I have B blocks. Otherwise, it is exactly the same formula. Okay, so just to make it clear, let's label this. So this is the sum of squares for A. This is the sum of squares for B, and then that last term, which is squeezed over there, is the sum of squares interaction. Okay, so that is how we decompose the treatment sum of squares into the three things. Remember the treatment, we're just rewriting the treatment using these three sets of parameters, and so these are the sum of squares associated with them, just like we saw in the interaction model. Okay, now the other two pieces, so we have treatment sum of squares, which now write as these three, and then the other part is we have a block sum of squares and the residual sum of squares. So the block sum of squares is actually quite simple. Again, just remembering that this is just another way of rewriting the RBD model. So we can just adapt that expression for the block sum of squares. So let me do that here next. So we just have to copy down residual and block sum of squares expressions from the RBD case and just rewrite it using these notations. Okay, so the first one is the residual. So let's write down the residual sum of squares. Actually, we already know what that is. It's this piece here. Okay, that's the numerator of the sigma squared estimate. So this actually we already have the RSS here. So let me just write that here just for completeness. So IJK observation minus treatment mean minus block mean plus overall mean. That's the residual sum of squares. And then block sum of squares is would be okay. So let's adapt the expression from RBD. So block sum of squares was to take the number of treatments. So that's T, which we now write as TA times TB. That's just another way of writing the treatments. And then we sum over. We do the block. We take all the block means, take the difference from the overall mean, and then sum them. So that just looks like summation over K. So overall blocks. So take the block mean. So that's Y bar dot dot K. That's everyone assigned to block K. That's mean of block K minus the overall mean square. Okay, so that is the block. That's the block sum of squares. It's exactly the same thing as in RBD. It's just rewritten using the two-factor notation. So number of treatments times the sum of all the squares of the block means from the overall mean. Okay, so that's the block sum of squares. All right, so those are all the sum of squares expressions, and so we know that from when we did block designs that treatment sum of squares plus block sum of squares plus residual sum of squares gives us the total sum of squares. And the only thing different here is we're taking the treatment sum of squares and breaking that further down into the three pieces for the main effective A, main effective B, and the interaction. Okay, so that's all we need in order to carry out our final set of ANOVA tables, and that is to now test firstly. So first we want to test, as usual, whether there are significant differences among treatments when there's blocking. So that's the first ANOVA table, and then second is, well, when there is significant difference among the treatments, let's then ask whether the interactions among the two factors are significant or not. Okay, so just like in the two-factor interaction case, we're going to have two versions of the ANOVA table. First, to test for differences among treatments, and then to ask whether, if there are differences, whether there is interaction. Okay, so let's go ahead and write down our final two ANOVA tables in this lecture series. Okay, so let's start here. Okay, so some space. Okay, so I'm gonna write down the two ANOVA tables, and then I'm gonna run through a list of all the hypotheses that we can test using these two ANOVA tables. Okay, so I don't need this anymore, so I wanted to give myself the entire board so I can fit both of the tables on here. Okay, so actually, there's not a whole lot of new things here. Really, I'm just taking the same two ANOVA tables from the two-factor interaction model and simply adding now a row for the blocks. Okay, so let's lay this out as follows. So let's start with the RBD ANOVA table for with T treatments, B blocks. B blocks. B blocks. Okay, so source, sum of squares, degrees of freedom, mean square, and then F statistic. Okay, so source. So when we did randomized block design, we had this ANOVA table. So we're just seeing it again, and I'm going to put it side by side with the version that allows for interaction. Okay, so treatments, blocks, and then residual. Okay, so again, I'll just write the shorthand because we've already seen all the algebraic expressions already. So treatment sum of squares, block sum of squares, and then residual sum of squares. Okay, I made the same mistake. I need some room to write the degrees of freedom. Okay, degrees of freedom, so treatment, so it's one less than the number of treatments. So we can do either just write T minus 1 or in our current notation, TA times TB minus 1. Blocks, okay, so there's one block constraint, so the degrees of freedom on the block is one less number of blocks, B minus 1. And the residual, we already wrote before, it's one less the number of treatments times one less the number of blocks. And so if you now we divide through sum of squares, divide by the degrees of freedom, we get the treatment mean square. We get the block mean square, and then we get the residual mean square. So in our notation, that's simply the estimate of sigma square. And so now from these statistics, we can do F tests. So we can do treatment mean square divided by sigma squared. That is the F statistic for testing whether there are significant differences among the treatments. Okay, and so now we realize that there's no mathematical difference between really treatments and blocks. It's really the interpretation. Block is a variable that affects the response, but we're not primarily interested in it, and so that's why we have that here to help control for the variability and make it easier to detect treatment effects for the experiment, which are the estimates that we do care about. Okay, but we know that we can also test for block if we like, so we can also do an F statistic for blocks, and so that would be a block mean square over the residual mean square. Okay, so that's the first ANOVA table, and so this is the ANOVA table for RBD that we've seen before, and now I'm going to put it next to the ANOVA table for RBD, but expressed as a two-factor with interaction model. Okay, so this is the second one, so RBD with factor A and B and interactions. Okay, so again, let's write the header, so source. Okay, so now again, I'm going to take the treatments and I'm going to break it down into the three component sum of squares. So I'm going to have A, B, and then the interaction. Okay, and then blocks, I'm just going to copy down, and residual, I will copy down. Okay, so remember that A, B, and the interaction corresponds to the treatments. Okay, so sum of squares. Okay, so we saw the expressions again, so we just use the shorthand. Sum of squares A, B, interaction, block, and then residual. Okay, degrees of freedom. So the degrees of freedom breaks down exactly as before. So remember that the total number of free parameters among the alphas, the lambdas, and the gammas exactly matches the number of treatment parameters that we would have seen. Okay, so there are T minus 1 free treatment parameters, and so that those degrees of freedom break down into A, B, and interaction exactly the same way as in the two-factor interaction model. Okay, so we have one less than levels of A, one constraint, okay, one less than the levels of B, and the interaction is, as we saw, is the product, one less of each, the number of levels multiplied together, And remember that if we add up these 3 degrees of freedom, we can check that it adds up to the degrees of freedom that we would have seen for separate treatments. Okay, so block sum of squares that has corresponding degrees of freedom. So the block degrees of freedom 1 less the number of blocks. There's 1 block constraint. And then residual, again, just copy from above. So from here we can get our mean square. Okay, so there's a comment that says someone wants coffee and chocolate donuts. Unfortunately, I can only provide that virtually. Can't provide, but hopefully you are enjoying the lecture. Okay, mean square, let's divide the sum of squares by degrees of freedom. So that would be the mean square for effect of A, mean square for B, mean square interaction. Then we have a block mean square, and then finally for residuals, as usual, let's write it as sigma squared hat. Okay, so that's those are the key statistics in our ANOVA table, and so from there we can now calculate our F statistic. Okay, so F statistics. So the pattern is quite straightforward. So to calculate the F statistic, you just take the mean square. For each row, you can calculate an F statistic. Just take the mean square and divide by sigma squared hat, and that gives the F statistic for the corresponding test of hypothesis. So this is mean square A over sigma squared hat, and then similarly for all of these rows. Okay, so those are our 4 F statistics. Okay, so those are the ANOVA tables. Okay, so I just want to point out a few things here in terms of what kind of hypotheses we can test. So first, of course, let's go back to the first table. This treatment mean square, so this F statistic, treatment mean squared divided by sigma squared, we know that one is very important, and that's usually the one we start with. Because this has all the treatments combined in one row, and so therefore this F statistic, as before, tests for whether there's any differences among treatments. Okay, so let's write that here. So this is the key F statistic we start with. Okay, so this is tests the null hypothesis of no differences among the treatments, all the T treatments. Okay, so that's usually the hypothesis test we start with. Okay, we ask whether there's any differences among the treatments. Okay, and so which F distribution do we use? We follow the pattern. So for this row of the ANOVA, so you're taking the F distribution with this numerator degrees of freedom and then this denominator degrees of freedom. So easy to remember is the residual degrees of freedom is always the denominator degrees of freedom in your F test. Okay, so this is these are the 2 degrees of freedom that we need for the F distribution for testing the hypothesis of no difference among treatments. Okay, so down here, well, let's also write down some of the other hypotheses we can test. So that's usually one we start with. And then, if there is significance, and now, from what we learned about interaction, this interaction F statistic is another one of interest. So if there are differences among the treatments, we can then ask, well, is there a significant interaction between the 2 factors? Okay, so I don't have enough room there, so let me do that here. So we can use the mean square interaction divided by sigma squared hat to test and the corresponding F distribution. So let me just write it out one to one. So the F distribution would have the corresponding degrees of freedom. So TA, TB minus 1, and then the residual degree of freedom. Okay, so we use that F statistic and then this F distribution to test the null hypothesis, which is that there's no significant interaction. So we can write it in terms of parameters. So the null hypothesis is that all the gammas are 0. So that's the formal hypothesis that's being tested. So that's the hypothesis for all I and j. So that's the hypothesis of no interaction. Okay, and so after you test interaction, well, if say interaction is not significant, then you can go and look at whether A and B themselves have a significant main effect, for instance. So there are F statistics that we can use to test that. So for example, we can also do the same thing to test for the effect of A. So I'm just going to write down one more. So let's say you can do the mean squared A divided by sigma squared hat and the corresponding F distribution. So what is that? It's F. So the numerator of degrees of freedom is now TA minus 1. Denominator is, as always, the residual one. TA, TB minus 1. Okay, so we can do that F test, and this is the meaning of it. This F statistic and this F distribution, we can use that to test whether there is a significant main effect. Okay, so that hypothesis. So what are the parameters associated with that? Well, that would be the parameters for factor A would be alpha I. So this is testing the hypothesis that alpha I is 0, that there is no effect of factor A. Okay, in words, this is testing no main effect of factor A. Okay, so you can see that there's you can use each of these F statistics to carry out a corresponding hypothesis test. Now, there's an order to which we should do this, and I've kind of alluded to that. But just to finish this off, I am going to write down the orders of doing the hypothesis test that we usually follow as kind of a flow chart, so we can keep track of everything. So I've kind of alluded to this already. So usually we start with the first ANOVA table. Okay, and we first ask if there's any differences among the treatments, and if there aren't any differences, well, then there's nothing else to investigate, because you don't need to investigate interactions or anything else, because we would simply conclude that these treatments have no effect on the response. Okay, and then we'd be done. Now, if there is a significant there are significant treatment effects, then we might then ask, well, is there interaction? And so then we would construct a second ANOVA table, and then use the interaction F statistic to investigate whether there's a significant interaction. Now, if there isn't, then we could throw out the interaction from the model and then reduce it to an additive, to a model with additive effects. Okay, so that's kind of the workflow that I've been alluding to. So just to finish up this section, I'm going to just take this off and just write down what I just said as sort of a flow chart, so it's easy to remember what hypotheses should be tested. Okay, so here's everything, and then this is the last thing I need to write down for this lecture. Okay, so let's call this our interaction flowchart. Okay, so first question to ask is, are there any differences among treatments? Among. the treatments. Okay, so if not, so no, if there is not, then we're done. There's nothing else to investigate. The experiment showed that the treatments we did the experiment with doesn't actually impact the response, so there's nothing else to do. Okay, so assuming there is a significant difference among the treatments, then we can now ask, is there a significant interaction? Okay, so that's the second, that's answered with the second ANOVA table. Is there a significant interaction? Okay, and so let's write down what I said. So if there is not, then we can drop the interaction terms from the model. So if not, then we can use additive effects model. Okay, so what that means is we delete the interaction term, so delete gamma on j from the model. Okay, and so what happens is when we delete the interaction terms, that takes out one row in the ANOVA table, and so you may not have noticed last time, but I'll just say it so it's clear now. So when we delete the interaction row from the ANOVA table, something has to happen to the sum of squares associated with the interaction term. Okay, so if we delete those parameters from the model, well, what happens to that sum of squares? Well, it shouldn't be too surprising that the interaction sum of squares just gets added back into the residual sum of squares. So let me just write it down so you don't miss this point. Okay, so when you delete the interaction parameters from the model, the sum of squares in that row, so the SSI, would get added to the residual. Okay, and remember that the whole reason we might delete the interaction is because it's not significant. So probably in this case, the sum of squares interaction is probably quite small anyway. So it's not going to have a huge effect when it's added back into the residual. So there's a question in chat that asks, the F statistics here, are they independent? Is looking at multiple p-values in multi-factor experiment overestimating a confidence level? So that is a very good point, which we are not able to thoroughly address within the constraints of this course. But yes, anytime you do multiple tests of hypothesis, so for example, if you find there is differences among the treatments and you follow up by doing a whole bunch of t-tests to ask whether different contrasts are significant or not, we run into the potential of this multiple comparisons problem. Okay, and so if you do, for example, if you do 20 t-tests, then just by chance, one of them is going to be significant at a 5% level, even if there's nothing going on. So we do run the risk of that, and that's something to be aware of if we're doing a lot of simultaneous hypothesis tests. In our case, we won't worry about that here. I only ever ask in this course to do a few follow-up t-tests. And so we're not going to worry about the multiple comparisons problem here. Although if you have many number of treatments, then that becomes an important question to address in the context of multivariate statistics. So that is a good point that was brought up here. Okay, so after you delete the interactions, then you can look at, as I was alluding to, you can look at the F statistics for A and B separately. So you can test if factors A and B are significant using their F statistics. Okay, so the last thing here is, well, if there is a significant interaction, then one way to show it is using a plot, and that's why we looked at interaction plots. Now, you might see lines that are not really parallel on the interaction plot, but remember those interaction plots are only a visual. It doesn't account for the variability across those means. And so in order to really assess whether there is a significant interaction, that's why we need hypothesis tests. But the interaction plot is a good visual, and so if there is indeed interaction, then we can make those plots to show how the interaction affects the response. Okay, so if we're done, we can visualize using interaction plots. Okay, so that's the last piece of notes that I need to give you. Now, is there anything special for the last lecture? Well, yes, there is firstly, there is a job that you guys need to do. So since we're coming to the end of the course, I do ask for you to provide your feedback for me on the course. And so let me put up the link as I get set up for our piano interlude. So let me put this link up. Okay, so your job while I'm getting set up is to go here, and I'll play a little bit longer today to give you some time to fill in this form and give me your thoughts on this course. Now, pieces for today. So I did promise I would do Clair de Lune. So I played it a few times over this last few days, and I'll get the sheet music out for that. And I will also play Chopin's heroic Polonaise. And then if I'm feeling okay about it, I will give La Campanella a shot to end off this segment. Okay, so I will get this set up while you load up that form. Okay, so hopefully you've all loaded it up. So let me switch to our piano angle now. I should also mention that some of you probably heard there was something funny with a couple of my. If your ear is astute, you might have noticed there's a couple of keys on my piano that sounded a little strange, and this is the reason for it. I have a couple of strings that have been snapped while practicing, and so one of them actually does affect is this D sharp, and so for La Campanella, of course, we hit this D sharp a lot, so the sound is a little bit off because that's the key. That's one of the keys that has a broken string. Okay, so for the last few minutes of today, I'm just going to do a quick run through of our last set of slides, and that's going to wrap up the material for our course. So just a quick example of factorial design with blocking. So imagine we have two factors for packaging a product, color and image, so 3 colors and two possible images. And so suppose there are 30 stores, and say we group them by, let's say, province, and so there's 5 blocks of 6 stores each, and then we randomly assign each of the 6 combination for the treatments to the 6 stores and measure sales. Okay, so just to illustrate, so suppose we have 2 images, one is of flag, one is of Queen Elizabeth, and then we have 3 colors. So those are the six different treatments. And so there's 30 stores, so we can actually lay out all the data. So this is exactly the 30 measurements that we'd be taking for each block and treatment combination. Okay, so there's 3 levels of A, 2 levels of B, 5 blocks, and so there's 30 total measurements. And so we can lay it out after we've collected the data, so you can look at this data after class, packaging, and so there you can put it in this way. So there's 5 blocks and 6 treatments, so there's 30 observations. And so as before, we have listed out the averages of each treatment, and then on the right hand side, these are the averages of the 5 blocks, and 824.9 is the overall average. And so we can ask, following the flow chart, let's first ask if there's any evidence of any difference among treatments, and then ask whether there is interaction. So in this context, interaction means this question down here. So is the effect of changing images the same for each color? So that would be interaction here. Okay, so first let's run through all the different ANOVA tables so you can see all the differences. Before we do that, we should look at the interaction plot. So there are 6 treatments. So here are the 6 treatments laid out as an interaction plot. Here are the means of each the combinations of color and image. So from this plot, at least, the lines are not parallel at all. It looks, in fact, they intersect here, which suggests that there is interaction. Now, in this case, these means are treatment means, but they're actually, in this case, instead of replicates, they're blocks. So in fact, each mean represents an average over blocks. And so, in fact, if we work out the normal distributions and the math of the normal distributions for this case, we find that the treatment mean, in fact, does not include any block effects, because the block effects actually sum to 0. So after averaging over all the blocks, there's no beta in this expression. Okay, so the treatment mean is normal with mean expressed by that particular treatment, and then a variance term that depends on the number of blocks we have. Okay, so why this formula is useful to point out here is because it means that the interaction plot can be interpreted in exactly the same way. There's no block effects hidden in this interaction plot. Each of these represents a treatment mean, and so we can interpret the interaction the same way as we did for the other model. Okay, so when we did the 2-factor model interaction, the interaction plots have exactly the same interpretation. Okay, so just to wrap it up, let's run through the different ANOVA tables. Okay, so here you see this ANOVA table simply has treatments, 1 row for treatments, and then residual. Okay, so the R command is this one, the top. So what is this ANOVA table? This one analyzes the data as if it was a completely randomized design. Okay, and so that's why there's only 1 row for treatments. We've combined all the 6 treatments, so that's why there's 5 treatment degrees of freedom. So this is the CRD analysis, completely randomized design analysis for 6 treatments. So is that the correct analysis here? Well, no, because this ignores the blocking variable. Okay, so you see here again we have the factor A colon factor B. Okay, and then you can wrap it using as factor. so that R will treat it as a factor rather than as a number. Okay, so this just takes the 6 treatments. So that's the ANOVA for CRD with 6 treatments. So of course, so here we forgot the block, so let's add in the block variable. So you see in the ANOVA equation, all we do here is we add as factor block. Okay, so we add in the blocking variable, and so we see in the corresponding ANOVA table that indeed the blocking variable is very significant. So where the store is located in this case has a large effect on the response. Okay, so in fact the block sum of squares is much larger than the treatment sum of squares. So here you see the treatment sum of squares is still just one line. So what analysis is this? Well, this is the RBD analysis. Okay, this is a randomized block design. We've put in the 6 treatments and the 5 blocks, and so we get the RBD ANOVA table. All right, so what we see so far is that if we forgot blocking, then we don't see any evidence of treatment effect. Okay, but once we put in the blocking variable, then there is a difference among the treatments. Okay, p-value is 0.04. So again, reminder that blocking is a variable that helps explain the response, and so if we put it in, and the blocking variable does in fact affect the response, then it makes it easier for us to detect differences among the treatments. Okay, so we've now seen you can do an F-test for blocks, even though often we don't worry about it, but the F-tests for blocks would show that the block effect is very significant, even though that's not our primary quantity of interest here. Okay, so following the flow chart, we saw there are significant differences among the treatments, so now let's check if there's interaction. Okay, so this is the ANOVA table that decomposes the treatment sum of squares into the 3 components, sum of squares for factor A, B, and the interaction. So you notice in terms of syntax, we just changed the colon to the asterisk here, and then R knows to separate it into the 3 components. Okay, so be careful here because the order might not be intuitive. So if you go through the order here, so color, so that's factor A, that's sum of squares A, and then we have factor B. And then R actually puts block before the interaction. So this is how we see the 3rd line is actually the block sum of squares. And then finally the last line is, you see the colon again, that's the interaction term. And you can match up the correct degrees of freedom by looking at the formulas we saw. Okay, so now that we've seen this ANOVA table, we just now go over to the F values. So these are the F statistics for each of these. And so you notice the usual test here is to look for interaction. So the interaction is the last row, and it is indeed significant. P-value 0.0479 if we're using a 0.05 level. Okay, and so this is this slide just kind of combines the 2 tables together. In R, we would construct them separately. So we would have so basically the treatment 50,000 comes from the ANOVA table with all the treatments combined, and then if we stack it together with this ANOVA table with the factors and interaction, then we can see clearly that the 50,000 from the first ANOVA table is equal to the 3 sum of squares from the factor A, factor B, and the interaction added together. Okay, and then the blocks and the residual rows are the same in both tables. Okay, so the interaction is significant. So in other words, we reject the null hypothesis that all the interaction parameters are 0. Okay, so here we found that there's an interaction effect, and so down here we see there is the interaction plot again. Okay, so if there's interaction, then it means that the effects of A and B should not be interpreted separately. Okay, and so why is that? Well, because when there is an interaction, the effect of one level depends on the level of the other factor. Okay, so the factors are dependent. Okay, so if you look at this interaction plot again, so remember the top line is the image of the queen, and so if you look at this plot, we cannot say that the queen image is always better. Okay, so we can't say image 2 is better than image 1. Okay, and why is that? Well, because whether that's true or not, well, depends on which color was used. So queen is better for 2 colors, and the flag was better for red, for example, here. Okay, so in other words, for simplicity, we do not try to interpret the main effect when there is interaction. Okay, because the effect of the level of one factor depends on the other. Okay, so I'm looking over at chat. There are no further questions, I believe. So that wraps up our material for this course. So that's the end of this lecture series. And so we will return on Friday with a review and a tutorial session. And you can also ask me anything at that point. So that will be for Friday. And so for now, hope you enjoyed this lecture series. And so if so, make sure you like and subscribe so you don't miss any future content, whether it's about stats or music or just other random things. All right, so I'm going to sign off for now, and we will see you on Friday.